Our next speaker is Erin Leonard. She got her Bachelor's of Science in Physics or Astrophysics. Astrophysics from the school up north, Berkeley. Yes. And got her PhD in planetary geology from UCLA. Go Bruins. Hopefully none of you are from Nebraska this weekend. That's okay. And has been at JPL for 5, 6, 7, less than a decade. Yeah. She is a planetary geologist with a focus on the geology and structure and evolution of ocean worlds. She is on the project science team for Europa Clipper. She is the deputy project scientist on a mission concept for New Frontiers. I think that covers it.
Okay, it occurred to me as I was, huh? Yeah, I turned it on. Is it not on? It's green. Okay. It occurred to me as I was putting together this talk, a couple of things. One, that there are several people in this room who have prominent roles on the Europa Clipper mission, and I think if you asked any of them, if you gave them this title, this talk, it would probably look quite different for each one. So maybe this should come with a bit of an asterisk and say this is Erin's version of lessons on Europa Clipper, or lessons and also looking forward to how we can potentially apply digital twin like models or like simulations to thinking about Europa Clipper in the future. So with that, I'm going to start with a little bit of an outline because it's going to be a fun and wild and fast journey on talking about Europa and Europa Clipper, and then tell you about a little bit of the punchline. So we're going to spend about a minute just making sure we're all on the same page about Europa and why we care about Europa and what we're doing going to Europa. We'll talk a little bit about the mission concepts before the mission, relating back to what Carl was just talking about with formulation and how we got to the mission that we have with Europa Clipper. We'll talk quite a lot about Europa Clipper and a lot about how the science drives the mission structure and the operations and how all of these things are really intricately linked together because of the science that we're trying to achieve. Then we'll talk specifically about some potential digital twin applications and hopefully have a good discussion about that as well. And then some, again, I would say my takeaways, Erin's takeaways on this. So if I was going to ask you to take one thing away from this talk, though, I'll say that the Europa Clipper's goal of understanding Europa's habitability requires this system-wide science and integration of diverse but synergistic data sets. And that's really mirrored in the mission design and the operation plan that we have. And I think hopefully I'll show you in the next while that all of those things are really intricately linked together. And that's why I think Europa Clipper and similar missions that study very synergistic science questions like this will benefit from digital twin applications. Okay, here we go. Okay, so we're gonna first make sure we're all on the same page about Europa. Europa is one of Jupiter's 4 main moons, also known as the Galilean satellites. It's actually the smallest of the Galilean satellites, but just barely. It's about the same size as our moon. It was discovered in 1610 by Galileo Galilei, and that's his sketch up there in the upper right of the Galilean moons and Jupiter. It was most of the things that we know about Europa, most of the big foundation that we have for the Jovian system was laid by the Galileo spacecraft, which was in the Jupiter system in the mid-90s to early 2000s. And it was really studying all of the Jupiter system together, but we learned some very crucial things about Europa from the Galileo spacecraft, and that is that its surface is extremely young. It's one of the youngest surfaces in the solar system. We think it's constantly being refreshed by some process. It's on average about 100 million years old, and that communication between the subsurface and the surface of Europa is really critical. And secondly, that Europa has a huge subsurface liquid water ocean that we think has aspects that are actually really similar to our ocean. And that really drove the question and drove the need for exploration of Europa after the Galileo mission. So we have water. we have heat, we have all sorts of fun chemistry. So what does that immediately make you think of? Hopefully your mind immediately goes to astrobiology and the potential for life, because that's where it went in the mid-90s and early 2000s for a lot of the scientists who were looking at Europa, and still does today, of course. So we have water, as I mentioned, much more than all of Earth's oceans, about twice the amount of water that we have on Earth all put together, but in the subsurface of Europa, a moon that's about the size of our moon here. We have essential elements that we think are essential for life. They're delivered both through impacts of the ice shell, and then that material is then transported to the subsurface through some sort of resurfacing process that we don't even totally understand, but that we know is happening because the surface is only on order 100 million years old. And then also from formation, just the interaction of that water and rock down at the base of the ocean in the interior. That chemical energy, which comes both from the water-rock interactions at the base of the ocean and also from the heat that's being generated within Europa. Europa is in a slightly elliptical orbit around Jupiter, and that creates a lot of friction within Europa itself. Europa almost breathes as it goes around Jupiter, and that creates a lot of heat in the interior and also contributes to that chemical energy. And then, of course, stability, all of this simmering together for 4 billion years. So we're going to talk a lot about Europa and Clipper, but I want to pause here really quick just to drive home this point that when we start thinking about looking for life and we start thinking about environments that may be habitable, you're going to immediately run into this wonderful but also very complicated issue of having to have all of these different pieces of science, all these different perspectives in order to answer this question. This is not a simple question. This is not something, we cannot send a life detector to Europa. That is not something that exists. And so this is really the foundation that we'll continue to talk about throughout this talk. So, touching on the many mission concepts to Europa, I'm not going to talk about these much in detail, but I really wanted to follow this up, especially following Carl and thinking about formulation. What eventually became the Europa Clipper mission went through many iterations, starting in the late 90s, in 1999, believe it or not. And that was with the Europa Orbiter concept, which was actually a Discovery class concept. So again, while Galileo spacecraft was still in the system, we were already formulating a mission to Europa because we knew it was that special. And I'm not going to say too much more about this besides the fact that the science objectives that were first developed for the Europa Orbiter mission and first developed by that science definition team can be directly traced through with some evolution to what ended up on Europa Clipper, and I think that's quite powerful. Next up, we had the Jupiter Icy Moons Orbiter, which for many reasons was ginormous, a nuclear electric propulsion type generated system, which they were very interested in the early 2000s, so now we're in circa 2003 here. The science definition team in 2003 was set to define goals and objectives for a mission to orbit each of the 3 icy Galilean satellites, so not just Europa, but also Ganymede and Callisto as well. This resulted in a mission concept that was over $27 billion in the early 2000s, but also a very thorough science definition team report, which we still look at some today when we're thinking about system science that can be done in the Jupiter system. But this is also what really pushed, I think, a lot of the current attitudes today, that is why our mission to Europa focuses on Europa and not everything in the system, because there are a lot of very interesting science questions, and as Carl pointed out, you will run out of money before you run out of science. The Europa Jupiter System mission, EJSM, was up next in circa 2010. Now this was really going after a collaboration between NASA and ESA, and the idea was that NASA would build this Jupiter Europa Orbiter, JEO, and that ESA would build the Jupiter Ganymede Orbiter, which would eventually become the JUICE mission that ESA did build and launch last year. However, the second Planetary Science Decadal Survey recommended that JEO's scope be reduced to make it less expensive, so this is sort of a great example of how the Planetary Decadal Survey also has big influence on what sorts of science questions and what missions end up being funded in the system. But there was a lot of work done for the Jupiter Orbiter Europa that still carries over. Following that, we had 3 Europa mission studies in 2011 after that second planetary decadal survey. And these 3 mission studies were a small but focused Europa orbiter, a Jupiter orbiting Europa multiple flyby mission, and a Europa lander. The Europa lander was found to be too expensive at the time, but the Europa study team that was in 2012 and community feedback from places like OPAG, the Outer Planets Assessment Group, found that the multiple flyby mission was probably the greatest science return per dollar. However, NASA headquarters wanted to keep both the focused Europa orbiter and the Europa multiple flyby mission in play, and that's actually I think a really interesting and unique part of this story, which I'm not going to have a lot of time to talk about today, but I'll mention briefly, and we'll continue to talk about it a little bit. But so in 2012, there was small augmentations that were studied it was called the Europa Enhancement Science Definition Team in 2012, as looking at small enhancements to either the focused Europa orbiter or the multiple flyby mission that would make them just a little more broad. In 2013, there was an instrument concepts for Europa exploration to continue to develop the instrumentation that could go on either mission concept. In 2014 was the instrument AO, the announcement of opportunity for instruments that could fly on either mission. So again, you're talking about, I just think this is really interesting from a formulation perspective, where you're essentially carrying 2 versions of a mission, a focused Europa orbiter, and I love Steve shaking his head here too, a multiple flyby mission. It's true, it's crazy though. And as an instrument, you're essentially proposing to both, or one, or just the other, and it was really quite crazy, and I don't really know why that happened actually, but it was a lot, right? And so you didn't find out until May of 2015 when instrument selections were announced that we were going with the Europa multiple flyby mission. And so you're carrying both of these missions throughout that whole process. We'll come back to this a little bit because there were a lot of things that kind of mirrored that even later in Phase A and Phase B, even Phase C of Europa Clipper. But this was the very short story of how we ended up with a Europa multiple flyby mission in 2015, and that's when Europa Clipper entered Phase A, or what would become Europa Clipper. Throughout this, the science was being developed, and like I said, you can really trace the origins of that science from that first Discovery class concept. But what we ended up with on our Europa multiple flyby mission was the overarching goal of exploring Europa to investigate its habitability. And you'll probably get sick of a lot of my buzzwords that I'll continue to use throughout this talk, but this is a holistic question, right? This is a question that drives you to have synergistic science, synergistic and diverse science. The science objectives are the ice shell in the ocean, to characterize the ice shell in any subsurface water, including its heterogeneity, ocean properties, and the nature of surface ice-ocean exchange. Composition, to understand the habitability of Europa's ocean and ice shell through the composition and chemistry. Geology, to understand the formation of surface features, including sites of recent or current activity and high science interest localities. And then current activity, I think of these more as really themes rather than objectives, but current activity really cross-cuts all of them through these 3 principal science objectives, looking at whether Europa is currently active in any of these areas. And you see this nice graphic on the right that Terry showed also, that I think is just a nice summary of the science that Europa Clipper was after. The interesting part, I think, about a flagship mission in particular when we're thinking about formulation is that you have a science definition team report, you have an instrument AO that goes out that is asking for instruments to be able to perform this science. But it doesn't tell you how you have to get there necessarily. It has ideas of how you have to get there, but it doesn't tell you how you have to get there. So from a science perspective on a flagship mission, you're setting the goal, you set the objectives, and then you get handed 9 instruments and say, okay, make it work. And that's really quite different than building a mission from the ground up where you're selecting the instruments that you need and the measurements that you need to fulfill those objectives. So I'm going to start with that. You had that science, and now you're handed these 9 instruments or 10 investigations with Europa Clipper. Okay, now go do your science, go. We can divide these up into the 5 remote sensing instruments and 5 in situ instruments, and I'm going to run through them really quickly just so that you can get an idea really of how diverse this mission really is. We have Europa UVS, the UV spectrograph, which is really our main plume detection instrument seeking plumes on Europa. We have ICE, the narrow angle camera, and the wide angle camera, which is really, of course, mapping this alien world, this amazing landscape that we have on Europa. MISE, the IR spectrometer, which was detecting the chemical fingerprints and really getting after the composition of the surface and potentially beneath as well. ETHEMIS, the thermal imager, searching for hot spots, and I always have to say this, like Predator. It's like Predator, but for, See, I've been giving too many public talks recently, so you can tell. REASON, the ice penetrating radar, which will be probing the ice shell, telling us about whether there's potentially water within the ice shell, and maybe even getting at that full thickness of the ice shell as well. The in situ instruments, we have mass specs, the mass spectrometer, which will be telling us about the atmospheric composition. SUDA, the dust analyzer, which will be telling us about the surface and potentially plume composition, if there are plumes indeed. ECM, the magnetometer, which is going to be revealing ocean properties and also that of the ice shell. PIMS, measuring the plasma environment and contributing to that measuring of the ocean properties and the induced magnetic field. And then lastly, but not least, why I keep saying 9 instruments but 10 investigations, we have the gravity radio science investigation, which is not an instrument. It uses the COM system to perform gravity science, Doppler gravity, and sense those interior layers and the interior structure of Europa. Okay, so I gave you the science and I gave you your instruments. Now go, right? Do your mission, do all the things. So this is what the result of that really is. And instead of an STM, we call this the P-staff because we love acronyms, and don't even ask me what it's an acronym for, I don't remember. But you can essentially think of this as Europa Clipper's version of an STM. Maybe Steve knows?
Project Science Traceability Alignment Framework.
There you go, okay. Okay, essentially the STM for Europa Clipper. We have our level 1 requirements over here. You can see a division of those science themes that I was talking about, things like the full depth subsurface exchange, the ice shell properties, the ocean properties, the regional composition, the atmospheric composition, landform geology, all the way down to surface activity evidence. The main reason for showing you this is to not go through all of the measurements and how we ended up getting from the instruments and all of the amazing measurements that they can make to understanding the habitability of Europa. We're not going to go through that, but what I really wanted to point out with this very, very simplified version of the P-staff is the interconnectedness. There are very few blank boxes here. We have if you're going in, the columns are all the different instruments, the rows are all the different science that we're doing. The color is indicating whether that instrument is primary, supporting, or an independent pathway to reaching that science or enhancing that. And there's so much interconnected here, so much synthesis that needs to happen between these data sets in order to reach those level 1s and fulfill the level 1 requirements, and in order to get after our goal of understanding Europa's habitability. And again, that's a theme that we'll continue to come back to. But first, we're going to go back to Europa Clipper itself. Okay, we had our science and we have our instruments. You've mushed it all together into an amazing mission now that's going to achieve amazing science. But what does that mean for the spacecraft? Because at the same time that we're mushing all this together into a mission that's reaching level 1s and to understand our goal of exploring Europa's habitability, we're also evolving the mission concept at the same time. So Europa Clipper entered phase A in 2015. By 2017, the Europa multiple flyby mission officially became Europa Clipper, even though we were already calling it that before, and it was officially adopted by NASA when it passed into phase B. There are a lot of things that happened between then. This is the same spacecraft, believe it or not, and it's not even what we ended up flying to Europa, right? So that Europa multiple flyby mission is there on the top. It doesn't have solar panels. It was nuclear powered to begin with. And that was something the instruments had to carry too into their proposals, was being able to go on a nuclear powered or a solar powered spacecraft, which is again something that's I find quite unfathomable. The bottom is what we ended up with as we were going into as we were in phase A, is the representation of Europa Clipper. You can see now we have solar panels, we have some amazing and really interesting engineering decisions that were made between then that have huge effects on the science and the operations of this mission that we will carry forward for the next 10 years. And none of those were good or bad, and I'm not trying to stand up here and say any of them were good or bad, but they all have effects on each other, and most of which were probably understood at the time, but not all. And that's something that I think we're going to continue to touch on as we talk about formulating missions and almost how the STM and the MTM end up really coming together, that blend of the two, and how decisions that are made on the engineering side trickle down into the science and trickle down all the way into the operations of the spacecraft. So some of the examples that I will just call out from Europa Clipper, where there were quite drastic changes were made during phase A and during design finalization that happened after instrument selection, after we had defined the science for the mission. And even some later into phase B and C include the changing from a nuclear powered to a solar powered spacecraft. I'm not sure there's a whole lot more I want to say on that, besides that if you ask an assortment of different engineers, they will end up debating the value of integrating the radar antennas onto a solar array. The radar antennas that need a very quiet electromagnetic interference and compatibility environment, and you're putting them on the solar panels that are generating the power for the spacecraft. Challenges that we will continue to always have through instrument development, through the mission design, and all the way into operations of the spacecraft. Later, the removal of the helium scalar vector magnetometer, you can see we had a magnetometer boom, we didn't have a magnetometer boom, we had a smaller magnetometer boom. Then after we removed the helium scalar vector magnetometer boom, you'll see that magnetometer boom is now 8.5 meters long. And we have to do rolling the spacecraft to continuously calibrate the fluxgate magnetometers that are there. A choice that was made for good reasons at the time. A lot of trickle-down effects into the science, a lot of trickle-down effects into the operations that we'll continue to see over the next 10 years. Most of those were known, the cost of which I think is not something that we had a great grasp on, and something that I still question whether that decision would have been made if we had had the full picture at the time. An interesting point that I always like to point out is that Clipper carried a relatively late decision on a launch vehicle for many different political reasons that we don't need to go into today, but there was a lot of design that went into the spacecraft carrying that they could go on any launch vehicle because we had not selected a launch vehicle at that time. And that was something that really heavily affected the design of the spacecraft and also how late that decision was made. Not necessarily things that we'll see continue to trickle down, but things that had big impacts on this mission as a whole. And that's really what I'm trying to say on this slide, is that all of these decisions had an impact on the science or the operations of the spacecraft, let alone the self-consistency within the mission design itself. They all presented their challenges. They were all studied very well at the time. But I think what I question is how well that synergy, the synergy between the science and the engineering side, the synergy that is translated from the mission design to the science to the operations of the spacecraft, whether we really fully understood that. And it will continue to shape the mission as we know it today. And this is the mission as we know it today. And we launched it, so we can't fiddle with it anymore, and that's great. We have now 5 solar panels on each side. We have an 8.5 meter magnetometer boom, as we discussed. We have our beautiful high gain antenna. We talked a lot about, or we've talked some about how we have produced these really synergistic data sets, and a lot of that has really fed into the mission design. So there has been a lot of success too in communicating between that synergistic science that we need and the mission design as we have it. And that's a really great example of that, is that all of our remote sensing instruments are pointed in the same direction. I think we should all just applaud for that, because it sounds obvious maybe, but it is not something that's ever been done before. And it's really, really insane, right? So we have all of our nadir pointing instruments, all of our remote sensing instruments pointing down at Europa, all taking data at the same time while we are performing flybys of Europa. And then, of course, I have to put my for scale over here. Our little astronaut is about the average size of a human, and so this is just a ginormous spacecraft. And I can't give a talk 3 weeks after the launch of Europa Clipper without playing a video of the launch, so you'll just have to bear with me because we don't have sound, so you'll have to make the sound effects in your head. But we counted down from 10. Yeah, there you go. There it is. And we have ignition, and we have liftoff. Oh my God, so beautiful. Barely a cloud in the sky, definitely no hurricanes or tornadoes to be seen. And at some point, if you corner me, I will tell you about all of the fun that happened when Milton tried to come view the launch. Hurricane Milton. Okay, great. Okay, so we launched this mission now. This is amazing, it's great, it's a huge achievement. What are we doing with it? We're going out around Mars, back around Earth, and out to Jupiter, and I haven't even updated this graphic yet. It still says we launched on 10/10, we launched on 10/14 because Hurricane Milton wanted to come to launch, but we told him no. Launched from Kennedy Space Center in Florida, and we will have Jupiter orbit insertion in April of 2030. This is a long-term mission. When we get to Jupiter, you'll see Europa come flying in here in purple. This is the Europa multiple flyby mission. This is not the Europa-focused Europa orbiter that we may have had at one point. So we are not in orbit around Europa, we're in orbit around Jupiter. And we do that because of the really intense radiation environment around Jupiter at the Europa orbit. And so you can see my little Geiger counter over here on the right. As we perform our very close flybys of Europa, our Geiger counter jumps way up. We increase our total ionizing dose down there in the red bar, but we're not increasing it as much as we would have, right, if we were in orbit around Europa. So this was the compromise that was made back in the day that we talked about, where we can have a longer mission, we can have a more thorough mission if we orbit Jupiter instead of orbiting Europa and having a shorter mission. And that's really driven by this radiation environment. Even though we're not orbiting Europa, we do end up with a really beautiful data set that gets really great coverage of Europa. And you're not really supposed to see what's over there on the right, besides the fact that it's a lot of purple and a lot of coverage of Europa. We end up with really great coverage of Europa with all of our remote sensing instruments just by having this global web of 49 flybys of Europa. And I'm going to take a quick minute to kind of show you a little bit of an example of how these data sets are built up to understand the habitability of Europa. So we have first gravity that's telling us something about the internal layers of Europa. So it's telling us maybe something about the thickness of the ice shell and the ocean together. Then we have the magnetometry and plasma that's telling us more details about the ocean, the properties of the ocean, the properties of the ice shell itself. We have imaging, so if you look at that little chaos area on the surface, we can now see it. We can understand the morphology of what's going on in the chaos terrain, whether there is exchange potentially involved between the surface and the subsurface within these chaos terrains. The infrared was telling us about that chemistry of those chaos terrains. What are the salts in those chaos terrains? Are they indicative of what might be coming from the ocean? What is it telling us about the composition of that ocean? The thermal environment telling us where Europa might be active within this chaos terrain, telling us where that heat is focused and what is the heat coming out of Europa. Radar and revealing to us what might be going on within the ice shell underneath those chaos terrains, and whether there might be liquid pockets of water or not, and how that affects our view of whether there are habitable environments within the ice shell or even just within the ocean. The ultraviolet, which is going to be looking at whether there are plumes coming from different sorts of terrains, including the chaos terrains, and the gas and dust mass spectroscopy, which is going to not only be telling us about what is in a plume if we happen to fly through it, but also what's being sputtered off the surface and getting us that really detailed analysis of that surface composition. And so here, the main reason I'm showing you this again is to really drive home that point that all of these data sets need to be integrated. All of these data sets, these diverse data sets, need to be integrated to give us our holistic picture of not only the ice shell, but the ocean underneath. And that science also really informs the necessary team structure that we have on Europa. One single instrument cannot determine Europa's habitability, and those integrable data sets will only come from a science team that is also well integrated. You cannot have instrument teams that are siloed, only caring about their own instruments or their own instrument data sets, and still produce very well synthesized science. And so that's really the driver behind the cross-investigation collaboration and all of the pathways that we put in place and that are used and practiced by the team today. A collaborative team environment is not a given, especially on a 200-person science team. And this is something we work really hard to support and nurture, and we do it now and we'll continue to do it for the next 10 years. This is not something you can put in place in 10 years and magically expect it to work. And this also drives how we aim to operate the spacecraft and tour, which we'll get to in just a second. But I want to say one more thing about the necessary team structure that we have. And one of the ways that we start to break out of the instrument silos, which are so easy to fall into because we're most familiar with our instrument team. And one of the ways we break out of this mold is through the thematic working groups. So all the COIs belong to the thematic working group that we call HAB, the Habitability Assessment Board. Everyone is a member of HAB because the goal of this mission is to understand the habitability of Europa. It is not to understand how thick the ice shell is. It is not to understand what the composition of Europa is. It is to understand the habitability of Europa. By breaking out into these groups, we provide high-level cross-instrument and cross-discipline science perspective that really drives us out of any potential instrument silo. It's how we coordinate tour evaluation, it's how we lead the strategic planning, and it's how we coordinate cross-instrument science analyses and publication. These are not driven through individual COIs or through individual instrument teams, but as a cross-investigation group. We also have the focus groups we also have the other thematic working groups, the objective thematic working groups that focus on composition, geology, and interior. All of those feed up into HAB because we are all HAB. The focus groups focus on things that are a little more specific to specific scientific interests, including radiation, reconnaissance, geodesy, and plumes. One other thing I wanted to mention here was just the management structure. I said these are not run by individual COIs and not run by individual investigations. And one of the ways that we ensure that is through rotating the co-chairs often. But that is a balance, right? We want to make sure we're maintaining some transfer of knowledge and transfer of information, but we also don't want to get stagnant and have certain loud voices continue to echo across the project. So here, I wanted to provide one quick example of how this feeds into the science operations that we have on the spacecraft. So I'm going to talk very briefly about the Strategic Science Planning Guide. And this is something we put together, we're still putting together, and we'll continue to put together until we get to Europa and even after that. But the first iteration of this was really driven through with a strong foundation in the science investigations that are kind of in the figure here in the bottom right. The science investigations feeding through the thematic working groups, evaluating the strategic plans and the science to be done in each flyby, putting that through the thematic working group leadership and HAB being synthesized by the Habitability Assessment Board, and then having that be an iteration of the strategic science plan. So this is, the operations of this mission have a strong foundation in the instrument operations, but they're not driven by the instrument operations. What else do I want to say about this? Yeah, we divide them up into two pieces, the nadir and the non-nadir. I'm not going to go into that too much, but the point I really wanted to get across here was that this holistic science necessitates holistic planning. We can't drive this with certain instruments. We have to drive this synthetically and as a team. So this team-wide input works to prevent investigation silos and orient the team towards achieving the unified goal of understanding habitability. And with that, I think comes a potential digital twin application. So I'm going to keep saying it with all my buzzwords. Habitability is a very holistic topic. It requires the understanding of many different and likely intertwined and interdependent aspects of a very dynamic, potentially very dynamic system. Europa Clipper produces these powerful synergistic data sets, but the interpretation of such data sets is not simple. Here's a nice simple example. It's really, though, just right, it's not this simple. So this is the example I like to think about of how we can be very simple and we can get at something like the ice shell thickness with Europa Clipper. We get at it through static gravity, tidal deformation, dual frequency magnetic induction, and radar radar penetration, which is a lower bound. And that's shown here in this lovely figure in the SSR paper by James Roberts in 2024, which is a great overview synthesis of some of the science that we're doing with Europa Clipper. And this makes it look really simple, right? If we combine all these data sets together, then we will have this really nice little gray box constraint on the thickness of Europa's ice shell. But there's a lot of not hidden, but there's just a lot of interdependency that's not shown in this figure, right? There's a lot of complication that goes into that, such as the composition of the ice shell. Are we all assuming the same thing for the composition of the ice shell? That's interesting because the radar is probably going to say that it changes from flyby to flyby. How are we getting to this integrated data set, this average ice shell thickness, when we have some data sets that are changing from flyby to flyby and some, like the magnetic induction, that are integrating data sets from all of the flybys to give us that answer? Not to mention, so there's a lot of complication that's sort of hidden up in here in this figure. This is just one pretty small, actually, aspect of the system that needs to be understood and then combined with others to understand the habitability of Europa. And I'll put up Steve's figure from the Habitability 2023 SSR paper, because I think this just shows very nicely all of the systems that have to come together, all of the things that you have to understand or pretend to understand about Europa to understand something about its habitability. Everything from the radiolysis, the exogenic material, the impacts, we have to have some sort of model of the ice shell. Again, that ice shell thickness that we just talked about is one very small aspect of that. We have to understand how material is being transferred within the ice shell to potentially the ocean and the subsurface ocean. And that involves understanding a lot of the processes that go into the surface geology that we have on Europa. And again, how all that material may get from the surface into the ocean, what the ocean's then doing with that material, right? And how that's being transported in the ocean, processed in the ocean, stratified, maybe convecting all together, whether things are precipitating out, whether they're not, and then how that all interacts with what's going down or what's going on in the rocky mantle of Europa, and how all of those things interconnect together. So you could call this just a very complicated simulation and not necessarily something that requires a digital twin. However, I think I would argue, and I think this is open for discussion, and maybe our interpretation of what a digital twin is, as Terry was telling us this morning, that we are making all these measurements, we're constantly learning something about the habitability of Europa, but also with that strategic science planning guide, we have the opportunity to take those things that we're learning about what our instruments are observing and how they're observing them, and feed that back into how we're operating the spacecraft. Whether there is a different way that we want to collect the data with our instruments, or maybe not a different area we're going to fly over because our tour is mostly set, or at least we don't talk about it not being set because that costs money. So, but how we're going to operate those instruments, or how we're going to change the way we observe Europa to continue to fill in some of the boxes here as we're learning about Europa. So that's Europa, at least in my head. But there's another aspect of a digital twin application that I think we would be remiss, of course, if we didn't talk about, and that's the spacecraft. As was mentioned several times today, the Europa Clipper spacecraft is designed to have simple operations. All of your instruments are on and taking data at the same time, and that's just again, an amazing achievement. And so operations are designed to be simple and repeatable and non-targeted, especially while we're in that nadir period, while we're in closest approach around Europa. That's not necessarily true when we're not in closest approach around Europa, and we have to deal with a lot of the other things, a lot of the other activities that are going on the spacecraft, like pointing. Where are we pointing? When are we downlinking data? When are we doing all these engineering activities? And also, when are we doing our non-nadir science? When are we searching for plumes? When are we understanding the magnetic field around Jupiter enough so that we can do the induction measurement at Europa? So there's a lot of things that still go into understanding the operations of even this simple and repeatable operated spacecraft. Additionally, while in formulation in phases A through D, I've talked about some of the decisions that I think were made that would have really benefited from a digital twin, mostly to make that process more rapid, and also to make sure that we understand the trickle-down effects that happen all the way into operations, and how those engineering decisions affect the science return ultimately, and how, again, we're going to operate the spacecraft, which translates directly into how much it costs to operate the spacecraft. The spacecraft is still really complex. It's actually very complex, and if I gave you the impression that it wasn't complex, then that's great, but it's really complex. And part failures can have significant trickle-down effects, and MOSFETs are a prime example of this, and if you thought I wasn't going to talk about MOSFETs, you're wrong. We're talking about MOSFETs, we're going there. So, metal oxide semiconductor field effect transistors, and I just had to laugh a little bit to myself, Terry, when you said earlier you did not go down to the level of transistors, and I'm going to suggest to you that maybe we should have gone down to the level of transistors. So we have over 1,000 of these transistors. They're located all over the spacecraft. And in May 2024, it was discovered, so this is, mind you, 5 months, less than 5 months before we were supposed to launch. It was discovered that some were not as radiation hard as expected. The damage happens gradually, it accumulates as the spacecraft mission progresses, and it could potentially result in these electronic switches, which is how I think of the transistors, being stuck, getting stuck on or stuck off. And there's no direct way to measure their degradation. Okay, you're launching a spacecraft in 4 months, 5 months, solve this problem. Solve this problem of over 1,000 transistors that are located all over the spacecraft that have 200 plus different applications, different circuits, different part numbers, different thermal environments, different radiation exposure, all of which now affect their performance, which you have no direct way to measure. Go. Sounds like a great opportunity for a digital twin. But no, it was a really great monumental effort, right? The team, of course, pulled this off. We launched the spacecraft. It was a monumental effort from the team over the summer of 2024 that included testing, modeling, science evaluation, all sorts of things that led to confidence that the mission is still going to be able to perform its full prime mission. We also added a new subsystem in 4 months called the Canary Box, which essentially contains a bunch of different MOSFETs of different applications, and now has the ability in that Canary Box to monitor how those MOSFETs are degrading. That's really great, but now you somehow need to understand what your Canary Box is telling you and how it relates to the other 1,000 MOSFETs all over the spacecraft. So there's still a huge task here, it is at least a necessary task, and this issue is inherently still tied to the ultimate science return of the mission. Even though we now have full confidence that we're going to succeed in the full prime mission, even with the degradation of the MOSFETs, it has the potential to affect operations. It has the potential to affect whether we need to be maintaining these MOSFETs in our non-nadir period, and it affects the science return. In addition, this affects the potential for an extended mission in a way that we don't fully understand yet. So a digital twin, in my mind, could be very helpful because we now have to relate these 1,000 plus MOSFETs all over the spacecraft to those MOSFETs that we can actually measure how they're degrading in the Canary Box, to the radiation data that we're collecting in the while Europa Clipper is in space. So we now have incoming data that's going to affect how we operate the spacecraft, that's going to affect this analogy that we have to make from the Canary Box to the MOSFETs all over the spacecraft. So even in Phase E, while of course we may have wished for a digital twin to help us make some of the big decisions that were made in Phases A through D, still in Phase E, we definitely could, I think, have a very applicable application for a digital twin. But I'm going to end with some takeaways here. Hopefully I've shown you that the scientific goal of Europa Clipper drives the structure of the mission, drives the structure of the science team, and all of these things are really intricately connected. Answering questions about the habitability of a body requires this really holistic and synergistic approach. And the spacecraft and the science team need to be structured in a way that enables that. It is not done by itself over here. The way that we designed the Europa Clipper mission enables this synergy, and we can continue to enable that synergy in the future to make sure that the science is achieved to its full capacity. And then I highlighted a couple of potential digital twin applications for Europa and Europa Clipper. The spacecraft could have definitely benefited from a digital twin in the design phase, where we really looked at how the design decisions that were being made trickled down into the science and trickled all the way down into the operations that we're going to be experiencing for the next 10 years. And how that all relates to cost in the long run, and not just costs in the short term. Late-breaking parts issues like MOSFETs, of course, we can't not talk about MOSFETs, is a direct application of a digital twin of the spacecraft that still will impact the science and operations of the spacecraft while it's at the target. And then I would also argue that whether we can quibble about whether it's the exact definition of a digital twin or not, the science of Europa Clipper will also benefit from this application. The synergistic abilities of the data sets may only be able to be fully explored in something like a digital twin that can really handle the both spatial and temporal variation that we're going to throw at it. And so I have my big takeaway statement here, which I won't repeat to you again. And with that, I'll thank you, and we can take questions and discussion.